We're going to talk about the nature of gases now. First, we need to get some terms clear. The kinetic theory. Now, kinetic means motion. Anytime you hear kinetic, it means motion. Kinetic energy is just energy of motion. So, if someone's moving very fast, they have kinetic energy. This line here has kinetic energy. It's moving. This one has much more kinetic energy. Moving much quicker, a lot more kinetic energy. This is going slow, less kinetic energy as opposed to that. Pretty cool. Now, particles in a gas are considered to be small hard spheres. The motion of particles in a gas is rapid and constant. And all the collisions between these gas molecules are perfectly elastic, meaning they will just bounce off each other. They don't smash into each other and just stick to each other. They just bounce off each other, and they're perfectly elastic, just like elastic or rubber balls bouncing off each other. They're not like Play-Doh where they'll stick together. The result of all these simultaneous collisions of billions of rapidly moving particles in a gas with an object is gas pressure. So all of these gas molecules are banging into each other, pushing and pushing and pushing. They're pushing against the walls. It's like if all these little gas molecules were students at fans at a varsity fan club concert. Or a Brock Storm concert, just pushing against the walls, just being crazy trying to get to the teen idols. That's how these gas molecules work, and they push and push and they bang into each other, and they're creating the pressure. No empty space, there's no particles there. And that's a vacuum. There's nothing around, there's nothing there, it's a vacuum. And there is, of course, if there's nothing there, there'd be no pressure. So I just want to talk a little bit about the atmosphere. You don't have to know this stuff, but just kind of have a comprehension about what is happening, what we have outside on top of us. So here we are. And on top of us is the atmosphere. And a lot of people think, well, air is nothing. But air is a bunch of gas molecules. Most of our atmosphere is actually nitrogen. About 79% of our atmosphere is nitrogen gas, 20% oxygen, and then some other trace amounts of other gases. But all these gases are acting like a fluid. They are a fluid. They are all pushing down on us. So we have atmospheric pressure. Now the higher you go up, it's like going higher toward the surface of a pool. It's less pressure. So at the bottom, there's much more pressure here due to all these gases just laying on top of us. Now the higher you go up, say if you're in Mount Everest, there's not as much fluid, not as much atmosphere on top of you, so it's lower pressure. As opposed to if you were even below sea level, it's even more pressure because of all this fluid on top of you. So atmospheric pressure will result from collisions of atom and molecules in air. All those molecules banging around and laying on top of us create an atmospheric pressure. Now, a barometer is a way that we can measure atmospheric pressure. If you can visualize here, we have all this air pressure pushing down, thus causing this mercury inside the barometer to rise. Now, the more pressure, the higher this barometer is going to go. The less pressure, the less the barometer will go. It's not going to go as high because there's not as much pressure. So the more particles on top of this barometer, and here too, the less it's going to rise. Now we have units of pressure. We have the Pascal, or Pa. Now how do I remember Pa, Pascal, as a unit of pressure? Well, who puts the pressure on you? Pa does. That's how my Pa Barron, used to put pressure on me. Another unit is atmospheres, and it's still another millimeters of mercury. One atmosphere equals 760 millimeters of mercury, which equals 101.3 kilopascals. Now, usually we'll use kilopascals or atmospheres. Now, the 760 millimeters of mercury came from that barometer, and that's how high that 1 atmosphere would push a barometer of mercury up, 760 millimeters, which is just 0.76 meters. Kinetic energy and temperature. Kinetic energy is directly related to temperature. If we look at this diagram here, it says air molecules will collide with the thermometer. Their energy is transferred to the mercury inside. Now the cold has much less kinetic energy. Air molecules will move slower in cold air, and mercury doesn't rise. Whereas molecules will move very rapidly in warm air, causing the mercury to rise, because the molecules will bang right into each other. And what happens when they bang into each other much faster? They spread out more. So if you can imagine the mercury in there, or the alcohol, most of our thermometers are alcohol now in our lab. They're all alcohol. The molecules inside, they get all this energy and they bang into each other, so they spread out. So you're spreading out, and then the thermometer will rise because the liquid inside the thermometer rises. Whereas opposed to the cold air, the molecules just slow. Just like when you guys are cold, you guys will kind of stick more to each other and don't want to spread out much. But if you're warm, you don't want to be close to each other. You spread out. I mean, that's the last thing you want to do, is be huddled up to someone trying to keep warm. You spread out and you move around a lot. When you're cold, you just contract. Just like when you have a door jam, a door will probably jam or stick more in the summer because the molecules inside that wood are moving quicker, so they expand. They bang into each other and they expand. Whereas in the winter, they move slower and they constrict. They come together. If you wear any jewelry, like a ring, when your hand is cold, it's much easier to take a ring off. Whereas if you're hot, your hand is actually going to be bigger. Your blood is going towards your hand. Your hands are bigger, and it's going to be harder to take that ring off. We look at kinetic energy and temperature here. So we do need to know this graph. We have percent of molecules, the number of molecules basically, more molecules up here, and then we have kinetic energy. So if it's cold, here we have the average. Most, if it's cold, have lower kinetic energy. So that's basically what this chart is saying. So we have a lot of kinetic energy up here, lots of Ke, and a little to zero, low Ke. If it's cold, most of the Ke, kinetic energy, most of the molecules have low Ke. But if it's hot, most of these molecules have a much higher kinetic energy. We're talking about the nature of liquids. Now, if we remember from the start of this semester, we talked about gases and liquids and solids. Remember, gases had no connection between the other gas molecules, whereas liquids do. They are connected to each other, and they had less kinetic energy than the gases. The difference of evaporation and boiling. So evaporation is where only those molecules with a certain minimum kinetic energy can escape from the surface of the liquid. Whereas boiling, all the particles throughout the liquid have enough kinetic energy to vaporize. So what does that mean? Well, let's look at an example. Here we have evaporation, here we have boiling. We look at these as molecules. These are all molecules of a liquid, and they're in a container. And here's molecules, liquid in the container on the right. Now in evaporation, what happens is just these molecules on the surface have enough energy to leave. It's like when you guys are leaving school, you do it in an orderly fashion. Or when there's a fire drill, you do it in an orderly fashion, one row at a time. Here's maybe the Seniors get to go. They're given enough energy to leave. And Sister Beers dismisses the juniors. They're given the energy to leave. And Sister Beers dismisses the sophomores. They're given the energy to leave. Then, orderly fashion, just the surface has enough energy to leave. It's like, and then we have the freshmen get enough energy to leave. Then the middle school. So just the surface has enough energy to leave. Whereas with boiling, boiling is like a varsity fan club concert. Everyone's going wild. Everyone's going crazy. All the molecules are going nutso. They got the varsity fan club up there performing. And everyone has enough energy to get to the top and get going to varsity fan club to leave their seats and get out. But because they're constrained by each other, it's like a mob mentality, mob rule here, they're constrained. They just can't all leave at once. Just because all the other molecules are in the way and the container is in the way. So if you imagine water boiling, all those water molecules have enough energy, have enough heat, 100 degrees Celsius, to leave. But what's keeping them is the water on top of them and the containers. Otherwise, boom, they'd all be gone. Just like at a varsity fan club concert. Everyone there has enough energy just to get to this front stage, but you just can't move past the rest of the crowd. You can't move past the building. Whereas evaporation, these guys down here at the very bottom, they don't have enough energy to escape. Only the top do. They're given the green light, so it's nice and orderly. In an open container evaporation, that's obviously these little molecules are going to leave. If we have an open container such as a lake, the molecules will evaporate, or if it's a puddle, the molecules will evaporate one by one from the top. But now if it's a closed container, what's going to happen? These molecules, they're going to try and leave. They're going to be given the go-ahead to leave, but boom, stop. They can't go anywhere. So what's going to happen is they're going to produce a pressure. They're going to go up, they're going to go back, down, and boom, boom, boom. They're a closed container, and there is going to be a pressure that's going to build inside because it's a closed system. If you ever have, I don't know if anyone's ever gone to a restaurant and had some water or anything, or had a glass or a bottle of water, and what happens in that closed system, they collect dew, not dew, but there's condensation, because after those molecules evaporate, there's nowhere to go, so they form with other molecules of water or liquid, and they will condensate. They will go back into liquid and kind of stick to the sides. As far as kinetic energy is concerned, when things evaporate, they actually leave the liquid at a lower kinetic energy. There's less energy there. They take with them heat and energy. So we have less kinetic energy down here. All that energy is leaving with that gas molecules. This is the purpose of sweating. You're a lacrosse player here, just an example. And you're really kind of tired, that's why you're panting here. So what happens? You sweat, you're hot. So you sweat on your forehead. What does that? So what do these water molecules have on your forehead? They carry heat. Now once these water molecules from your forehead evaporate, they take heat with it. So they take heat with it, and you cool down. That's the purpose of sweating. So when your sweat evaporates, it's cool because it takes the heat. Let's compare this. If you've ever gone to a nice dry climate, sweating works really well because things will evaporate very easily in a dry climate. But if it's really, really humid, there's a lot of water molecules in the air, you don't really sweat. You sweat a lot, but you don't evaporate. The water doesn't tend to evaporate as much, so you can't cool off as much.